In our tutorial, we will be focusing on 7 predictor or independent variables, which are included here. Now, if we recall, we had 23 variables in our existing data set, one of those being the value of the house and another being the GOID, which we need to retain both of those. So let's subset out our data. So we will select the variables we'll be working with just to simplify our tibble. So we'll give it our existing tibble using the pipe and the select function. We will just name each of the variables we want to retain. And we're going to save this as SD for San Diego _ houses. Now that we've done that, we could view the data. Make sure to spell it right. And here we go. We have our GOID, which we'll use later on, the house value, which is important to our model, and then our 1, 2, 3, 4, 5, 6, 7 attributes that we're interested in. Now, before we move any further, we want to look for kind of strange values, such as maybe a 0 value where there was no information collected, but it wasn't represented as a missing data or something like that. So let's just run the summary function on our variables. And when I look, I see our GOID. These numbers make sense, their range, the house value. Now we know that there would be no census tract with a minimum value of 0, a value of 0. So we want to kind of remove these. Years built, we know houses aren't infinitely old, and then we suspect every house to have at least one room. The proportion of bad plumbing, this is okay to be 0 because there can easily be census tracts where all of the houses have good plumbing. So let's filter out some of those rows or observations. So here we'll just save it as the same name, SD _ houses, and we will filter the year built, and we want only those rows where a year built is greater than 0. And we also want rows where the house value is greater than 0, the number of rooms is greater than 0, and the number of bedrooms is greater than 0. So we know all of these should have at least a value of 1 or larger, or for example, year built, probably in about the 1960s. So if we run this filter function to filter out rows, we can then rerun our summary, and now we see that these values make a bit more sense. So let's move forward. Now we see that this value of 0.65, this is probably represented by a collection of condos where some of them are bachelor apartments with no bedrooms, which is fine, and then ones with bedrooms, and they've taken the average because it's the average number of bedrooms. Okay. Now that we've prepared our data, we need to we'll do our graphical analysis pre-check. So we want to use our scatter plots to check for linear relationships between predictors and dependent variables, our dependent variable. We want to use our box plots to look for outliers, and then we'll use our histogram to look and ensure our variables are normally distributed. Okay. So I'm going to demonstrate this using both ggplot and base R for one variable, and then you will just do this for the remainder of the variables that you have. Base R plots are fine for this variable review because really in any analysis we're not going to be producing these for our report. So let's look at our scatter plot, and we'll look at year built to house value. So we're using the geometry of point, and then we will fit the line of best fit for our linear model, and we just won't include the standard errors around that. And here we see somewhat of not a very strong trend, but there is a bit of a trend in year built to the house value. We could do the same in base R by giving us our plot and calling out the variables that we want to use. Now we're using in this case, we call the tibble and use the $ operator to point to the variable name that we're interested in, or to select out the column. We do that twice. And then we want to include that same regression line. So what we need to do, it's a bit more complex, is actually fit the regression model and then use the AB line function to add that line to our plot. And there's our same plot. Now we can see that the ggplot defaults are quite a bit nicer, as we understand, compared to base R. We'll do the same for our box plot. Now, when you're creating our box plot on one variable in ggplot, we need to just set x equal to nothing in our aesthetics mapping and then give y. Okay. Now we see one outlier here. It's not significantly above. It is based on our interquartile range idea. It does seem outside as an outlier. For this scenario, we don't have any justification to remove it, so we will leave it in there. But just remember that we have one value with, kind of outside of the normal range there, based on number of bedrooms. And we can do our box plot very simply by just using the box plot function and then pointing it to our variable. And the last thing we will do is our histogram here in ggplot. Now it gives us this warning about picking a different value for bin width. This is fine for us because we're just simply using this as a sort of an exploratory analysis. And we can do that same plot, not as nicely, but in base R using the hist function. We could also test using a normality test instead of these histograms. And for this example, we can use our SD housing data, and we're just going to get rid of the GOUID temporarily here because we don't need to test that. And if we use our map function here, we could map each histogram. So I'll just show us what that looks like. And in your case, they would all be in the viewer. But here are different histograms. Now it's a little tricky because we'd have to recall which value this is when we're using this. But we could also change this to our Shapiro test. We have not loaded our Shapiro test. So let's try and figure out how we would do that. So let's look in help, and if we use 2 question marks, it will search in all packages. Oh, but what the mistake is actually a spelling mistake, and it's not that it's not loaded. So we'll just change that. And the map function allows us to apply a function to each of the variables in our tibble. And here we go. So for house value, we see that, and when we looked at housing value, we see it's not normally distributed. When we look at house value using this test, we see that it is not normally distributed. We can reject the null hypothesis that our data is normally distributed, as our p-value in this test is much, much lower than 0.05. And we won't look at the rest for now, but you can go through those. let's do some data transformation on our house value. So we will set it up as a new tibble or new variable name called SD underscore trans, just to remember that these are our transform variables. And we have feed it in our SD houses tibble. Using the pipe, I can then mutate our variables to create these new variables. And for our first one, I'll use the log of value for the variable name. And what that is using the log function. I'm taking the house value, adding 1 to it, so we don't get negative infinity values. And here we'll mutate this to create a log version. Okay? And you can chain on multiple mutates here with the pipe, but for now we won't mutate others. We'll quickly run this. And if we looked at that, and it is our log value, we can see that is approaching more of a normal distribution. And this is fine, as we know that the linear regression model is fairly robust. And here we have a set of chain mutations here. So I'm actually going to mutate the data for a number of our variables. So I will stop the video here and let you put this into your code. And if you notice, I'm dropping the original variables by using the select function and putting the negative sign in front of them. So I'm going to drop each of these variables in my final data set. So I run that, and we'll catch up in the next video.